Hey everyone, we're going to do a lab today. I'm going to be doing the physical part of it, the moving of the spring and so on. We're going to be measuring the speed of a wave in a spring two different ways. So one way is going to be the direct measurement, just using velocity equals distance over time. And the other way is going to be using V equals F lambda, the universal wave equation. All right, and then you can compare the results between the two, and so you can compare two experimental results. So here's the setup. Okay, I've got a distance measured out with a measuring tape. So the spring's going to be stretched from there to there, and I'm going to be sending a wave down and so on. I'll be doing all of the activity part of it. You're going to be doing the measurements. So the first measurement you're going to be doing is in here. Get that so you can see it well here. You're going to get the length of the spring measured out. So there's your centimeter scale, 480, and you're going to judge what kind of measurement you want, what kind of significant digits you think you can get, how many decimal places and so on. So I'm aiming for it to be right at that black line of the tile. Okay, so that's the first measurement for the lab. Let me get my camera set up in the tripod here. All right, so then all I have to do is send a wave down. And so the direct measurement is I'm going to send a pulse down, put that spring down at the bottom of this leg here. So we can stay consistent if it fell later on, to change the tension slightly or something. So here we go. The first kind is if I just send a pulse down. And so I'm going to send a bunch of those. And your task is going to be to measure how long it takes the wave in the spring to travel a certain distance. I'll just keep doing that over and over again. Each one of these measurements would be considered like a trial. And so right, so each one you can measure a bunch, and then of course tabulate them all on a table. And actually, I probably should do a mark, set, go kind of thing. So you mark, get set, go. You mark, get set, go. Make it easier for you to do. You mark, get set, go. You mark, get set, go. You mark, get set, oh, that one didn't work. You mark, get set, go. You mark, oh, I did it again. Getting excited here. You mark, get set, go. Mark, get set, go. Mark, get set, go. And so hopefully I'm doing a good enough job there of making those waves. You can just watch each section of the video as many times as you need to get some measurements, but I want measurements of distinct wave pulses so you can have a bunch of numbers. Okay, so that's your direct measurement part of the lab. Should be able to get the speed of the wave in the spring. Okay, so the indirect method is using standing waves and eventually V equals F lambda. Okay, so what I'm going to do for that one is I'm going to set up a standing wave. I'll probably skip this one. I don't know. Let's do it, I guess. So if I set up a standing wave, the problem usually I skip this one because there's a ton of friction and springs kind of rolling and stuff. So let's just see if we should ignore it or not. If it looks like it's an outlier in the data, you've seen maybe that in math class in grade 9. So I have a standing wave going, and then from the class you can figure out, you can do your analysis of like how many loops that is, obviously one loop, how much of a wavelength that is. You know the distance, because we're talking about the distance from this mark here all the way to the end. And so if I go the specific frequency needed to maintain that fundamental mode of vibration, you can measure the frequency of it, and you know the wavelength, and so you can calculate the speed. So this one I don't necessarily think is going to be as trustable, but certainly you can compare. So when you're measuring the timing of this this is where you want to think of it like, maybe you think of it as like when the spring gets out to the end, think of it as like, okay, start the stopwatch. There's 1 cycle, 2 cycles, 3 cycles, 4 cycles, 5 cycles, 6 cycles, 7 cycles, 8 cycles, 9 cycles, 10 cycles. So maybe you time for 10 cycles and you do a bunch of measurements of that starting at different times in the video. Just basically like you would do in a lab. You'd be like, your lab partner's doing this for a while and you just measure times. Okay, so that was the fundamental pattern, single loop. So basically a wavelength you can calculate based on that. And then we're going to do a 2-loop pattern next. And there's a very specific frequency I have to maintain for this. I'm just doing a video for a class, so just give me a minute, okay, Ethan? All right, so this one here. Again, we could say start to stopwatch 1, 2, 3, 4, 5 kind of thing. Okay, so I'll just let you do your thing. Measuring times for a certain number of cycles, whatever you choose to collect as your data. And obviously there's a wavelength associated with this pattern fitting into this length. And there's a frequency you're going to measure, and you'll be able to calculate the speed of the wave. Hopefully that's enough time. Let's do a 3-loop pattern now, same deal. This one's a lot faster, but you'd be like, okay, start off 1, 2, 3, right? So start 1, 2, 3, 4, 5, 6, kind of thing. Time to get some good measurements there. And then we'll try for 4, and then that'll be it. This one might be harder to measure because it's so fast, but do your best. You can hear the sound over there, you can use that as a guide. Start 1, 2, 3, 4, 5 kind of thing. And that's all you need for measurements to get the speed of the wave in the spring. Have fun.